the quality indicators per question. And then I'll hand it over to Emily, who will start off with 5-digit data quality flags, then move on to confidence intervals, and lastly, discuss how to use confidence intervals for statistical hypothesis testing. So the 2021 census has two main components, that being a short form questionnaire and a long form questionnaire. So the short form questionnaire is known as the 2A, and this is given to 75% of dwellings in the country. The questions on the short form 2A will be referred to as short form content throughout this presentation. The long form questionnaire has two different types, the 2AL and the 2AR. Both of these questionnaires contain all of the questions from the 2A, plus some additional long form, plus additional questions, and these will be referred to as long form content. So the 2AL was given to 25% of private dwellings in the country, and these dwellings were selected using a systematic sampling design. The 2AR, on the other hand, is given to 100% of private dwellings that were located in First Nations communities, Métis settlements, Inuit regions, and other remote areas. So the main takeaway here, and something to keep in mind, is that the short form questions were given to 100% of dwellings, and the long form questions were given to a sample of 25% of dwellings. So in the census and in surveys in general, we have two types of non-response, that being total non-response, or TNR, and partial non-response. TNR occurs when a dwelling received a questionnaire but left all of their questions unanswered, or when they returned their questionnaire, but that questionnaire did not meet the minimum amount of content. So for the census, our minimum content standards state that at least one question has to be answered aside from the roster question. So the roster question is just that first question on the questionnaire, which asks you to list all of the members of your dwelling. Partial non-response, on the other hand, occurs when some of the questions were answered, but then some of them were left unanswered. So we can experience TNR and partial non-response in both the long form or short form content. So why is non-response an issue in surveys and in the census? So the reason is because it can be a potential source of bias in census counts and in long form estimates. So a bias due to non-response could occur if the characteristics of respondents are different from the characteristics of non-respondents. So just to illustrate this, if we think about telephone surveys, generally respondents to telephone surveys tend to be older than non-respondents. And further, age can be related to various characteristics like income, education, work experience, etc. So we can see there's potential issue that could arise here in this context due to non-response. So generally, we can't measure bias because we don't know what are the characteristics of non-respondents since we don't have data for them. But I do want to mention, without going into the technical details, that it's often the case that a non-response bias can be corrected or addressed with the use of rich auxiliary information. So this leads us naturally into today's first quality indicator, which is the total non-response rate. So the TNR rate indicates the risk and its potential magnitude that a bias may have been introduced due to total non-response. This is the primary quality indicator for the 2021 census, and it accompanies each of our disseminated outputs and products. So the TNR rate is replacing what's known as the global non-response rate, which was used in 2016 and in previous census cycles. The GNR rate accounted for both partial and total non-response, whereas as the name suggests, the TNR rate is only accounting for total non-response. In the 2021 census, we did account for partial non-response through the creation of quality indicators per question. So this will be discussed in the next section of the presentation. The TNR rate is calculated at the household level, and we have two definitions of the TNR rate. The short form rate, which is computed for short form content, and the long form rate, which is computed for long form content. The TNR rates are calculated for a POI, or population of interest. And a POI simply corresponds to a set of either long form or short form households that are in a given geography. Okay, so here we have the formal definition of the short form TNR rate. So for a given POI, the short form TNR rate is simply the percentage of total non-responding households in the POI. And very similar, we have the long form rate, which is almost the same as the short form rate, with the minor detail that the survey design weights are used inside of the calculation in order to weight it. So here we have an example of a data quality pertaining to one of our disseminated products, which is a census profile. So for the province of Quebec, if we look at the second row, we can see that Quebec has a short form TNR rate of 2.9% and a long form TNR rate of 3.7%. So the link here at the bottom of the slide will bring you to our Statistics Canada webpage, which has an interactive tool for building census profiles. So as a general recommendation, we advise that analysts and users of census data exercise caution when using either short form or long form data that has their respective short form or long form TNR rate above 50%. Okay, so now I would like to talk about the quality indicators per question. So these are data quality measures, which are specific to each question on the questionnaire. And they quantify two related sources of error, that being non-response and imputation. So when we talk about questions, questions can be either at the household level or the person level, and this will depend upon the characteristic that the question is trying to measure. So for example, questions asking about household income would be at the household level, and questions asking about a person's highest level of education would be at the person level. So these question level quality indicators are calculated over the set of units in a given POI, which are said to be in scope to the question. So all that really means is if the question is not applicable to that person or that household, then that person or household would be excluded from the calculation. So just to illustrate, questions regarding labor would be out of scope or not applicable to persons who are less than 15 years of age. So these question level quality indicators, or quality indicators per question, are disseminated in their own standalone data tables. And these are disseminated for most of the questions asked on the short form and for key income variables on the long form, and are also produced for many of the standard geographic areas used in the census. So the set of tables that were disseminated are for various short form and long form variables and geographies that are likely to be of high interest to analysts and data users. The row doesn't stop there though. So more complex tables for different variables or different geographies are available upon custom request. So the link here at the bottom will bring you to, again, our Statistics Canada webpage, which just has a list of all of the data tables for the question level quality indicators that we disseminated for the 2021 census. So here I'll introduce the short form quality indicators per question. So we have two of them, the non-response rate for the question and the imputation rate for the question. So the non-response rate is the proportion of units in the POI who did not respond to that particular question. And the imputation rate is the proportion of units, of in-scope units in the POI, whose response to that question was imputed. So here's just an example of what a short form question level quality indicator table would look like, or does look like. So in the columns, we have the non-response and imputation rates for a few different short form questions. So we have sex at birth, gender, and age. And in the rows, we have different levels of geography. So it usually starts with Canada, then we have Newfoundland and Labrador, and the level of granularity increases, so to census divisions and census subdivisions. And I do want to point out, so since this is a short form table, we also have the short form total non-response rate for each of the geographies here in the second column. Here are the long form question level quality indicators. So in total, we have 3 of them. 2 of them are the same as the short form, that being the non-response rate and the imputation rate. And again, I just want to note here, similar to the long form TNR rate, we use the survey weights inside of the calculation here for the long form rates. Here's the final long form rate. It's called the impact of imputation rate, and this is only available for income variables. If y is a variable from some income question, then its impact of imputation is the proportion of the total of y values which have been imputed. So we can think about it's like a proportion, but instead we're using a continuous variable or a numeric variable instead of a categorical one. This slide here provides a little bit more technical detail about the impact of imputation rate. We won't be going over this in today's presentation, but there's a small example here if you're curious or if you would like to know more. So I would like to just wrap up this section by saying a few words on, as an analyst or a data user, how can we interpret non-response and imputation rates? So as I mentioned earlier in the presentation, the TNR rate and as well now the non-response rates per question indicate the risk and magnitude that a bias may have been introduced by non-response. So in general, a lower non-response rate would indicate that there is a lower risk of non-response bias, and therefore when using the data, we can be more certain that the figures and estimates are reliable. However, both the TNR rate and the applicable question level rates should be consulted in unison as they may offer differing perspectives on the quality of the data. So as an example, there may be a certain geography that has a very low total non-response rate, but for some reason, let's say their labor questions exhibit a very high non-response rate. So when trying to do analysis and drawing inferences from labor data, we would want to exercise caution in this context. So lastly, when comparing the TNR rate and the non-response rates per question, users should just be aware of how they differ in terms of their definitions. So when it comes to interpreting imputation rates, we can see these as an indication of whether or not the quantity of imputed values is large relative to the quantity of reported values. And when we think about the impact of imputation, we can think about it in the exact same way, but instead of quantity, replace it by the sum. So generally, the higher that these rates are, the more reason there is to question the quality of the estimates and the data and the potential for bias. However, I do want to be very clear here that the imputation rates themselves do not indicate the quality of the imputed data. They simply provide an indication or measure of how much of the data has been imputed. So for the 2021 census, our imputation models used used auxiliary information that is well correlated with the variable to be imputed. So therefore, on average, we expect the imputed values to be accurate. Okay, so I would like to now hand it over to my colleague, Emily, who will start with the discussion about 5-digit data quality flags.
Thanks, Alex. So as Alex mentioned, the next quality indicator we'd like to present is the 5-digit data quality flags. So these are 5-digit codes that give a broad sort of at-a-glance indication of data quality for a given area. And in this slide, we have an example showing the code for the rural municipality of Sherbrooke, Prince Edward Island. So in this area, the 5-digit flag is 00909. And the images give a reminder about where to find this code. So in tables on the website by clicking on the information button, or in Beyond 2020 format shown in the bottom right of the slide. So the 5-digit flags are available for tabulations based on place of residence geographies. And each digit in the code has a separate meaning relating to data quality for either the short form or the long form. And I'll just briefly go through the digits and their interpretation. So the first digit is the incomplete enumeration indicator. For all censuses, there are some reserves and settlements where enumeration can't be completed, and census data aren't available for these areas. So 0 is the default value for the first digit of the 5-digit flags. And it means that the area is not and does not contain an incompletely enumerated reserve or settlement. The second digit indicates the range of the short form TNR rate, or it can indicate if data in the area were suppressed to meet the confidentiality requirements of the Statistics Act. So again, 0 is the default value. And for this digit, it indicates a short form TNR rate of less than 10%. And you can see, in fact, in the information box that the short form TNR rate for this area is 2.6%. And so you don't need to rely on the data quality flag for information about TNR rates because the rates themselves are also published. But for some applications, it can be helpful to have the information about data quality summarized in a code. And then the fourth digit of the flag is the long form TNR rate indicator. So the same as the second digit, but for the long form TNR rate. Finally, the third and fifth digits of the 5-digit flag are the short form and long form income suppression indicators. So the disclosure control rules for income variables are different than for other variables. So we have separate indicators for income data suppression. And actually, the area of Sherbrooke PEI is a small population area where both short form and long form income data had to be suppressed for confidentiality. So that's why this household income table shown on the slide doesn't contain numeric values. And the 9 in that digit of the 5-digit flags indicates income suppression for the short form. And then lastly, the 9 in the 5th digit indicates that long form income data have also been suppressed. So the complete table listing the possible values for the digits of the data quality flag and their meanings is provided in the Census data quality guidelines on our website. Just a few things to keep in mind about the data quality flags. So firstly, a 0 in any of the digits is the default value, which would indicate the lowest range of TNR rates or no suppression, depending on the digit. A value of 9 for the TNR rate indicators or for the income suppression indicators indicates suppression to meet confidentiality requirements. And a 5 for the TNR rate indicators indicates a TNR rate of over 50%. And as Alex mentioned, in that case, the data should really be used with caution. So in past census cycles, there was suppression based on data quality, which meant that in those rare cases where there was a GNR rate of over 50%, data would be suppressed. For 2021, quality-based suppression was eliminated. So that means the user has the choice of how to use the data in the case of high TNR, but we do advise caution in those cases. And Now we'll move on to confidence intervals for long-form estimates, which are the final quality indicator we'd like to present in the webinar. So confidence intervals fall into the broader class of variance-based quality indicators. So first I'll mention some general facts about variance and variance estimates for the long form. Variance is a measure of uncertainty of estimates produced from a sample. It's a quantity we estimate for long form estimates, but not for short form estimates. And the details of how we estimate variance for the long form are not terribly important for working with variance-based quality indicators, but I'll just mention that the type of method that we use to estimate variance is a replication method. So the variance estimates for the long form have a different meaning depending on the type of sampling in the area. So in most areas of the country, we sample 25% of households. And in these areas, the variance estimates measure the variance due to sampling and total non-response. In the other areas where we sample 100% of households, there is no variance due to sampling, and the variance estimates measure the variance due to total non-response. So something to note about variance is that variance estimates on their own are difficult to interpret. And that's partly because variance doesn't have the same scale as the estimate itself. So generally, people use variance to construct other quality indicators, which are easier to interpret. And examples of those include standard errors, coefficients of variation, and confidence intervals. So something that's new for the 2021 census is that confidence intervals are available as the variance-based quality indicator for long-form estimates. And the advantage of confidence intervals over other variance-based indicators, and the reason confidence intervals were chosen for the 2021 census, is that they allow users to easily make statistical inferences. Uh, the confidence intervals are usually available in data tables containing long form estimates that are accessible through the Statistics Canada website. There are three exceptions to this where, because of technical limitations, the confidence intervals aren't included in the disseminated tables, but they're usually available by custom request. So these exceptions are disaggregated data tables with a very large number of cells, tables that contain data from multiple census cycles, and tables that include both short form and long form estimates. So next we'll go over some basic definitions and concepts related to confidence intervals. And the table on the right of the slide is a snippet of a table with mobility data on the website, showing confidence intervals in the second and third column. So this table shows counts of people who lived in Alberta 1 year before the census, and the counts are broken down by their current province of residence. This is long-form data, so confidence intervals are available. But for the tables on the website, the confidence intervals are a statistic that you do have to go in and add manually. So just to cover some basics, first of all, what do we mean by a confidence interval? So a confidence interval for an estimate is an interval constructed around the estimate which reflects the uncertainty. And to represent that uncertainty, instead of just giving the estimate itself, we provide a range or an interval of values. And a confidence interval is expressed by two numbers, which are the lower and upper bounds of the interval. And these are the numbers in the second and third column of the table shown. So for instance, if I look at the second row of data in the table, the row for Newfoundland and Labrador, the estimate of people who lived in Alberta 1 year previous to census day is 1,545. And the lower bound of the confidence interval in the second column is 1,337. And then the upper bound in the third column is 1,786. So in order to make sense of a confidence interval, we need to know its confidence level, which is a number expressed as a percentage. And the confidence level for the confidence intervals provided with long form estimates is 95%. And intuitively, we can think of this as the degree to which we can be confident that the interval contains the true population value. So for a 95% confidence interval, we could say that we're 95% confident that the interval contains the true population value. In this slide, we have a diagram which gives a more precise depiction of the meaning of confidence intervals and the confidence level. At the top of the picture, there's a confidence interval showing the estimate and the true population value, which in this case is contained in the confidence interval. But the estimate and the confidence interval depend on the sample we draw. And the sampling is a random process, and different samples will generally result in different estimates and different confidence intervals. So in the box with the dashed line around it, we've shown estimates and confidence intervals that might in theory be produced if we were to hypothetically repeat the sampling and estimation procedures again and again. And all of these intervals in the box with the dashed line around it contain the true population value except for the one shown in yellow. And in fact, for a 95% confidence interval, if we repeat the sampling and estimation procedures many, many times, in the long run, approximately 95% of the intervals produced will contain the true population value. So that's the precise meaning of the confidence interval and the confidence level. So now let's move on to how confidence intervals are constructed. So the most basic method of computing confidence intervals is called the Wald method. And here the population parameter of interest is called theta. So for example, theta might be the count of people in a given area who are immigrants. And the estimate of the parameter is theta with a hat. And you may be familiar with confidence intervals that you get by adding and subtracting 1.96 times the standard error from the estimate. So these are Wald intervals. More precisely, the lower and upper bound of a 95% Wald confidence interval are given by adding and subtracting z times the standard error of theta hat. From the estimate theta hat. So here Z is the 97.5th percentile of the standard normal distribution, which is approximately equal to 1.96. And the standard error is the square root of the variance estimate. So the assumption of, oops, sorry, I didn't cover the bottom line of the previous slide, which is very important. So I wanted to say that this confidence interval method, the Wald method, is a very common way of constructing confidence intervals, but it makes a strong assumption, which is that the sampling distribution of the estimator is a normal distribution. So this assumption of normality that we make for the Wald interval is actually often violated in practice. And in particular, this is an issue for small sample sizes and for proportion and count statistics. So for the census, we actually use more elaborate confidence interval methods, but we also included the Wald interval in this presentation because it's helpful to be able to relate these other methods to the Wald interval. For long form estimates, the method used to construct confidence intervals depends on the type of statistic. For all statistics other than proportions and counts, we use the student's confidence interval. For proportions, we use the modified Wilson confidence interval for proportions. And for counts, we use the modified Wilson confidence interval for counts. And research and simulations have been done to ensure that confidence intervals for long form estimates are constructed using methods which achieve coverage close to the stated confidence level in most scenarios. So, in other words, if we were to repeat the sampling and estimation procedures a very large number of times, the actual percentage of those intervals that contain the true population value is close to the confidence level. So the first method used to construct confidence intervals for long form estimates is the student confidence interval. And again, this is the method used for all statistics other than proportions and counts. And the form of this interval is very similar to the walled interval. So I'll only point out the one difference here, which is that this interval is based on a student's t-distribution rather than a normal distribution. So instead of a z appearing in the formulas for the lower and upper bound of the interval, there's a t, which is the 97.5th percentile of a student's t-distribution. And the student's t-distribution is a probability distribution which has one parameter called the number of degrees of freedom of the distribution. And for the census, we approximate the number of degrees of freedom by R, which is the number of replicates used for variance estimation. And for disseminated data products, R is equal to 32. For small sample sizes, the student's confidence interval has better coverage than the walled interval. And another property of this interval is that when the number of degrees of freedom is large, the walled and the student's intervals will be very similar. And the second confidence interval method that's used for the census is the modified Wilson confidence interval for proportions. And what's probably most evident from the slide is that the formulas for the bounds of this interval are more complicated than for the walled and the student intervals. And this has to do with the sampling distribution for proportion statistics. But the main thing to keep in mind is that this interval, which is more complex to define, has better properties. And in particular, it has better coverage than the Walden student intervals. So the formula on the slide is really just here for your reference if you're interested, but I'm not going to go through it because, as I say, it's really the properties of the interval that are important and not so much the formulas. Um, One important feature of this interval is that it's not symmetric around the estimate p hat, unlike the walled and student intervals. And I'll emphasize that a big advantage of this interval is that it has better coverage than the walled and student intervals for small sample sizes and when the population proportion is near 0 or near 1. And the last method that's used to construct confidence intervals for the census is the modified Wilson confidence interval for counts. So this is a method that was developed by Statistics Canada researchers specifically for the 2021 census. And the development is similar to the modified Wilson confidence interval for proportions. It applies when the population parameter of interest is a count. And again, I won't go through the formulas, but they're here for your reference. I will mention that even though this is a similar method to the method on the previous slide for proportions, the formulas do look quite different because this particular method relies on an approximation. So like the interval for proportions, this is an asymmetric interval. And it has better coverage than the Walden student intervals for small sample sizes, and when the population count is near 0 or near the population size. So those were the three methods we use to compute confidence intervals. And finally, we'll discuss how confidence intervals are related to hypothesis testing and how confidence intervals can be used to perform hypothesis tests. So statistical hypothesis testing is a method of statistical inference that can be used to decide if data gathered from a sample support a hypothesis about a population parameter. And the general setup is that we start with two hypotheses about a population parameter. The first hypothesis is denoted H0, and it's called the null hypothesis. And we think of this as a default or a status quo hypothesis. And the other hypothesis is the alternative hypothesis, which is a statement that can be thought of as a scientific or an analytical discovery. So usually analysts want to show that the data support rejecting the null hypothesis because this amounts to making a new discovery from the data. And as a toy example, the null hypothesis could be the statement that in a given geographic area, the proportion of people in 2021 whose highest level of education was a bachelor's degree was equal to the proportion in 2016. And if we denote the proportion for 2021 by P 2021 and the proportion for 2016 by P 2016, we can write this hypothesis as P 2021 equals P 2016. And then the alternative hypothesis is that in the geographic area, these two proportions aren't equal. So in other words, P 2021 is not equal to P 2016. And to perform the hypothesis test, we need a way of deciding which hypothesis the data support. And this is given by the rejection criterion, which is a criterion involving quantities computed from the sample that's used to decide whether or not to reject the null hypothesis. So in the example where the null hypothesis is that P 2021 is equal to P 2016, the rejection criterion might tell us to reject the null hypothesis if the estimates of those proportions are far from each other. Or in other words, we would reject H0 if the absolute value of P hat 2021 minus P hat 2016 is large enough, where we would then have to define what we mean by large enough. And how we define that would depend on what's called the significance level of the test. And this is the probability of rejecting H0 when H0 is actually true. So ideally, we want to reject H0 only when H0 is false and not reject H0 only when it's true. But since we only have the data from the sample to go on, our test won't be perfect, but we can insist that at least have a low probability of an error of the type where we reject the null hypothesis when it's actually true. And that probability of rejecting the null hypothesis when it's actually true is called the significance level. And it's a quantity that's fixed by the analyst, and it's often set to 0.05. So now confidence intervals can in fact be used to do hypothesis testing. And this slide explains how the two concepts are related. So this works when we have a hypothesis test that's of this simple form shown on the slide. So here H0 says that the population parameter theta is equal to a fixed value, theta 0. And HA says that theta is not equal to theta 0. So for this kind of test, a confidence interval for theta hat actually provides a rejection criterion for rejecting the null hypothesis. And the picture shows how this works. So here we've got a 95% confidence interval for theta hat. Then if we want to do this hypothesis test at significance level 0.05, what we need to do is reject H0 if theta 0 is outside of the confidence interval. So in other words, we reject H0 if theta hat is far from theta 0, where the notion of far is actually defined by the confidence interval. So far is being outside the confidence interval. So H0 says that theta is equal to theta 0. But if based on the data from our sample, our estimate of theta is so far from theta 0 that theta 0 isn't even in the confidence interval, then we can reject H0 at level 0.05. Okay, so finally, we'll see how we could use this method to check if the difference between two estimates is statistically significant. And for this, we'll come back to the example where we're interested in comparing the proportions of people in 2016 and in 2021 whose highest level of education was a bachelor's degree. So specifically, we want to test the null hypothesis that these two proportions are equal against the alternative hypothesis that they're not equal. And we want to perform the test at the 0.05 level. So to make this test appear in the same form as we saw in the previous slide, I've put both proportions on the left side of the equation. So we're testing the null hypothesis that P 2021 minus P 2016 equals 0 against the alternative hypothesis that P 2021 minus P 2016 is not equal to 0. And I'll mention that this particular test requires an estimate for the difference of these proportions and a confidence interval for that difference, which aren't provided in disseminated products. So this would involve making a custom request to get those values. But suppose we've done that and we have those values, and the estimates we have are p hat 2021 equals 0.230 and p hat 2016 equals 0.195. So we can see that the estimates are different, but we know that there's uncertainty associated with these estimates. So what we're really asking in doing this test is, given this uncertainty, is the difference between the estimates statistically significant? In other words, is it reasonable to conclude that the difference in the estimates reflects a difference in the true population values? So to do the test, we need to use an estimate of the difference, P 2021 minus P 2016, which is equal to 0.035. And the basic idea now is that we want to reject the null hypothesis if this estimate of P 2021 minus P 2016 is far enough from 0, and far enough will be defined by the confidence interval. So for this hypothesis test, we need to use a 95% confidence interval for the difference. So if we have this interval from the custom request and it has lower bound 0.025 and upper bound 0.045, then to do the test, we just need to check if 0 is in the interval. So since 0 is smaller than 0.025, it's not in the confidence interval. And this means we can reject the null hypothesis at level 0.05. So that is, we reject the hypothesis that the proportion of people in 2021 whose highest level of education is a bachelor's degree is equal to the proportion in 2016. So that brings us to the conclusion of the presentation. So as we saw, many data quality indicators are provided with 2021 census data products. And many of these quality indicators are new for the 2021 census. It's good to keep in mind that overall census data quality is very good, but it's recommended that users consider the whole suite of quality indicators when they're assessing the relevance of census data for their specific use cases. And in particular, confidence intervals for long-form estimates can be used for statistical inference. For more information on data quality indicators, we have the link here to the 2021 Census Data Quality Guidelines on our website. In our list of references on this slide, I'd really like to highlight the Census Data Quality Guidelines, which was the document linked on the previous slide. So it covers most of the material in today's presentation. And this final slide gives some information about Statistics Canada's data service centers. So I would guess this group is largely familiar with our data service centers, but there's some information on the slide about some of the services that are offered, as well as contact information for inquiries. So thank you for your attention, and we'd be happy to answer questions.
Great, thank you so much, Alex and Emily, for sharing that presentation. Were there any questions for either of our presenters today? Well, the first comment in the chat is, yeah, and I would echo this as well. Thank you so much for distilling this really complex information in such a clear, concise way. I know you definitely threw a lot of material at us, but yeah, the delivery was excellent. So I applaud you for that. Thank you so much. There is a question in the chat asking how different are these methods from the 2016 quality indicators?
Yeah, I guess I could start to unravel that a little bit. So as I mentioned in my part of the presentation, the total non-response rate for the 2021 census was replacing as the main quality indicator the GNR rate, or the global non-response rate. So I kind of made the distinction about the types of non-response they account for. And then we did add the question level quality indicators to supplement the fact that TNR rates did not account for the partial non-response. And as well, we have new for the census this year, the inclusion of confidence intervals as well. So I don't know if Vincent or Emily wanted to add to that at all.
Yeah, I was going to jump back in one way or the other on that question. So it's a pretty significant overhaul. The effort was really to put more power in the hands of the user, but that also can feel overwhelming for some users. But essentially, for the GNR versus the new TNR plus item level indicators, for example, essentially we disaggregated the quality information into a lot more granular information that we make available to users. And for confidence intervals, this is a motion that StatCan as a whole has engaged into. So it's not only the census, it's more broad, with the effort in mind always to be more user-centric. So try to remove some layers of effort that you need to do in order to do statistical inference. But on the technical level and on the implementation level on our end, it's a very colossal undertaking. So yeah, it's information you could have figured out to a degree with the standard errors that were available in 2016, but that are now in a much more readily functional manner available to you.
Great, thanks, Vincent, for adding that additional information. There's another question in the chat. So around slide 25, are there any metrics for quality of imputation? Are the imputation models publicly available?
As far as I'm aware, I don't believe we published the models. I think Vincent might know a little bit more about this than I do.
Yeah, this is a bit outside our usual wheelhouse. You will find some information, but not the precise model specification in each individual subject matter, subject-specific guides. And usually they're the ones receiving and answering questions through either the help desk or I assume the data service center email box if any questions were to be asked about specific imputation models. And as far as metrics for quality of the imputation, I'm not sure what you're really asking there. If you're asking for thresholds where it's good or bad, akin to the 50% threshold for GNR, again, everything related to bias indicators is on a continuum. There's never really any hard rule. Usually when I'm supporting internal users with this, what I'm usually suggesting is assume or wish for that we've addressed bias through non-response modeling and imputation models, but you as the subject matter that is knowledgeable of the data you're analyzing because you have knowledge of local area information and such, if you find yourself confronted with information that contradicts what you think should be true, then start looking at those quality indicators, and maybe if the imputation rate is high, you start having the reasoning that maybe it's due to non-response bias not being fully corrected for through our response modeling.
Justin, does that answer your question? Perfect, thank you. Just another question in the chat. So are the GNR and TNR at all comparable, like even approximately?
Emily, go ahead.
Yeah, I suppose I can say a little bit about that. So there isn't a simple analytical formula that would relate the two. Conceptually, the way they're defined is fairly different, given that GNR takes into account both partial non-response and total non-response. And also household size factors into GNR and not into TNR. The effect of that would be minimal for like on the large scale for large populations. So there isn't a simple very simple way to compare them, but as you would expect, they're strongly correlated. So if you're comparing a GNR from 2016 to a TNR rate for 2021, there are basically two reasons that would account for the difference, which is like the actual difference in non-response, and then the difference due to just the difference in definitions between GNR and TNR. What we recommend is that if the difference between a GNR and TNR is less than 5%, to effectively treat them as being equivalent, being, representing the same level of non-response. I don't know if Vincent would like to add anything to that.
No, not much. I mean, with the work we've conducted internally, because we were expecting questions like that, I guess GNR 2016 GNR equals 2021 TNR plus 5, or 2016 TNR plus 5% was a rough linear relationship. But again, there's, as Emily mentioned, a lot of variance for other reasons, but that's essentially the shorthand that we're telling users. There's a note to that effect in the Census data quality guidelines.
Perfect, thank you. So another question. For statistical inference using confidence intervals with the long forward questions, do you recommend looking at whether confidence intervals overlap as a quick way to determine statistical significance?
I'll jump on that one again. So the short answer is no. Generally speaking, we'd go that route more out of lack of alternative options. So for instance, Emily discussed significant difference for estimates between 2016 and 2021, but for say different domains, but within the same cycle. Currently, it's not fully supported by the system. And in that case, with an internal user, we had the same discussion and we essentially fell back on that. The reason why we're not recommending it is because it's not, well, for starters, it's generally taught to be a conservative method, which means analysts will make fewer significant discoveries. But more practically, there are larger issues with, especially when comparing two estimates that are not independent, which would be true for most pair of estimates that arise from the same census. because there's a covariance term that is not accounted for, that's beyond the scope of this presentation. But that's the reason why we want to bring users towards custom request estimates of difference with CI of difference, to have, rather than a quick way or rather than a shorthand, have a more formal or a more thorough method to evaluate statistical significance.
Great. Yeah, thank you for clarifying that. Were there any other questions in our final few minutes here today? Perfect. Well, I don't see any other questions in the chat. I'd like to thank again Alex and Emily and Vincent for being here today and leading us through this presentation. As I said before, the recording and the slides will all be made available on the Community Data Program website in the coming days, so that will be an ongoing reference for you as you're working with the 2021 statistics or the census. So yeah, a big thanks to everyone. Thanks again to StatsCan. We always appreciate having you folks in to present, and yeah, thanks for all you coming, and we'll look forward to seeing you all next time.
Thank you very much. We're also on our end very happy to empower data users to use the new information more and more.
Perfect. And Tala, you can probably stop the recording now. And as I said, I'll be posting